So we saw the k-mean algorithm, which was a deterministic approach for the clustering problem, where we minimize the sum of square distances between every data point and the its respective cluster parameters, which can be given by this cost function over here, j equals to the mean over r and mu, where r is the assignment variable and mu is the cluster centers and or the cluster parameters, and we are going to minimize over the total sum of the sum of square difference according to each one of the assignment of xn minus mu k square over here. And we saw that this can be done in a alternative way or alternating way in the k-mean algorithm, where in the first step, the assignment step, we simply optimize over r and k, and in the second step we optimize over mu k while keeping the other respective variable fixed. And here in this particular case here, the k-mean algorithm that we have looked at is actually a deterministic algorithm. This means that what this essentially means is that we only have a 1 of k assignment or 1 of k coding to r and k, and we do not assign any uncertainty to this particular r and k, and this is also otherwise known as the hard assignment. What this means is that every time, since if you recall that matrix of r and k, where each row over here represents the nth observation, and I'm going to assign this to my 1 out of the k classes, where only one of them, the sum of this r and k over here, has to be equals to 1. This means that for each data point, we are only allowing it to be assigned to one particular cluster, and all the rest of this has to be assigned 0. So this is in other words, a hard assignment where we are not maintaining any probabilistic distribution to this particular hard assignment over here. Neither are we assigning any distribution or any probabilistic distribution to the centroid here, where we are simply, for each one of the cluster, we are simply treating them as just represented by one particular point of mu k over here, and there's no distribution. There's no particular distribution to this particular the class or this particular cluster in our k-mean algorithm. So the obvious question to ask now is that, can we actually do better than a hard assignment, and can we actually do it with what we have learned so far using a probabilistic approach? The answer is actually yes, and we will see that this will in turn be modeled as a probabilistic distribution of what I have introduced in the very first part of the lecture, where we are going to look at the joint distribution of x, z conditioned upon theta. Here, theta here would be my unknown parameters. The unknown parameters, that we will see that these unknown parameters would be the centroid as well as the distribution, or in other words, if we assume that this is a Gaussian parameter or Gaussian distribution or whichever other distribution that we have, we will parameterize this with a set of uncertainty or a set of unknown parameters, and then the assignment parameter that we see here in this particular k-mean example here is a hard assignment, so we denote it as r, but probabilistically we can denote this as z over here, which can be represented as a set of latent representation. So here, we'll see that instead of a hard assignment where it's 1 out of k coding, where every one of this assignment, 0 or 1, we have 100% certainty. So this means that this guy here in my k-mean is a deterministic algorithm where every one of these assignment I will have 100% certainty. But in the probabilistic distribution, or in the probabilistic case, every one of this z, we'll see that it will also take 0 or 1. It will also take 1 out of k assignment. So z and k will take 0 or 1. We will see that in a few slides time. And then what happens here is that we will also assign a certain probabilistic distribution to each one of my z. This means that I won't hard code it, or I won't hard assign it to be 0 or 1. I will give it a certain certainty of value to be 0 or 1 here. And of course, x over here would be our observed data, which is the same as what we have seen earlier on in the k-mean algorithm. Now, before I go into the detail of this, the probabilistic assignment that we have seen, or the probabilistic distribution that we have defined in the previous slide, and how to solve it using the expectation maximization algorithm, let me first introduce the concept of Gaussian mixture model, which we will see that it helps us to model clusters in the later part of this lecture. And now there's a very famous place in the Yellowstone Park in the US, and in that particular park there is a very famous spring or hot spring called the Old Faithful, where at every regular interval this Old Faithful, it will there will be a fountain that looks something like this. Actually, this was a picture that was taken from by one of my PhD students when she visited this place several years ago, two years ago. And here we can see that what's interesting here is that if we plot this particular Old Faithful data set, which consists of 272 measurements of the eruption at this Yellowstone Park, and if we were to plot them out in this fashion, where the x-axis here represents the eruption time in minutes. So this in this region here, closest to this region here, means that the eruption time, the duration of the eruption, is actually very short. And the closest to the higher end here, it means that the eruption duration is actually over extended periods of time. And the y-axis of this of every data over here would be the time in minutes to the next eruption. So now suppose that I observe this data set over here, xn over here. This means that the data eruption time would be somewhere in the range of 1.6 minutes. So it will erupt for 1.6 minutes, and after I observe this, the time in minutes to the next eruption would be about 62 minutes, for example. And so if I were to plot this out, this is the distribution that I will observe here. All the green points would be all the data points, a two-dimensional data point of x1 all the way to xn that I observe here. So these are in the two-dimensional space, where it's the eruption in time in minutes as well as the time in minutes to the next eruption. And we can see that in this particular case over here, if we were to use a Gaussian distribution to describe this particular data set, it will be inappropriate, because a single Gaussian or a unimodal distribution here. So a single Gaussian is a unimodal distribution with just one peak over here, would be insufficient to model this distribution, which obviously is a bimodal distribution. This means that there are actually two peaks or two centers to this particular distribution over here. And what we can see here is that a linear superposition of two Gaussians would in fact be better able to characterize this particular Old Faithful data set better, because it's a bimodal distribution data set. And at this point, we should be able to get some intuition on how it relates to our previous clustering problem that we solved using k-mean. So each one of this Gaussian distribution over here, it's going to be a cluster. So this is going to be k equals to 1, and this is going to be k equals to 2, for example. Now, we've seen that mixture distributions of taking a linear combinations of Gaussian can be, it's also known as the Gaussian mixture model, or in short, the GMM. And this linear combination is in fact sufficient. Given sufficient number of the Gaussians, it can give rise to very complex distribution or very complex density that we can actually use to model any continuous density with arbitrary accuracy. Now, here's an example where we have a trimodal distribution, or simply a multimodal distribution given by this red curve over here. So this is our probability of Px over here, and we can see that if we were to fit this using one single Gaussian distribution, this wouldn't be sufficient to model this probability distribution of Px, where it's obviously a trimodal distribution with 3 peaks. So an obvious outcome of this, or obvious replacement of the unimodal Gaussian distribution, would be to simply model this particular distribution with 3 Gaussian distribution, or a linear combination of 3 Gaussian distributions. So a linear combination would actually arise, or will result in this particular complicated distribution over here. And we can see that this in fact can also work for any dimension. For example, in two-dimension feature space or two-dimensional space, you can see that if we have 3 Gaussian distribution, a superposition or a linear superposition of these 3 Gaussian distributions over here, parameterized by each respective set of parameters. So what this means is that each one of these Gaussian, it has their own respective mu1 sigma 1, for example, and then mu2 sigma 2, and as well as mu3 sigma 3. So this all these 6 values over here, or these 3 sets of values over here, they need not necessarily be the same. And taking a superposition or a linear combination, we'll see later that taking a linear combination, this means that we are taking a weighted sum of this. So we have n of x and mu1 sigma 1 plus n of xn mu2 sigma 2 plus n of x and mu3 sigma 3. So a linear position means that we have to weigh each one of these into our probability distribution. So we'll see that we'll have something that is called a mixing coefficient over here, which is denoted as pi 1, pi 2, and pi 3. So to take a weighted sum of this, where the sum of all the pi's should be equals to 1 to give rise to this linear combination. And here in these 2 examples here, we can see that linear combinations of these Gaussians can already give rise to a very sophisticated distribution that can allow us to model multimodal distributions. Now, the probability distribution, or more formally, the probability distribution of a Gaussian mixture model is given by the superposition of k Gaussian densities, which I have illustrated in the earlier slide, that the joint probability distribution of x is equals to the sum of the linear combinations of all the respective components of the Gaussians. So in this case here, we can evaluate it to be pi 1, the normal distribution of x, mu1 sigma 1, plus all the way to pi k, the normal distribution of x, mu k, and sigma k over here. So here pi over here is what we call the mixing coefficient, and it has to be from 0 to 1, as well as it has to all sum out to be 1. So here, since each one of this is a respective component of a Gaussian distribution, we can see that the end result of this is simply a linear combination or a weighted sum of all the contributions of the Gaussian distribution. So for example, if I have 2 Gaussian distributions over here, what happens here is that I have a point which I call xn over here. Then I would have to evaluate xn according to the distribution of mu1 and sigma 1, as well as mu2 and sigma 2. So I have to put it through the normal distribution twice. I mean the 2 respective normal distribution, as well as weighting it using the coefficient, using the mixing coefficient of pi 1 and pi 2. So this means that how much each respective normal distribution or Gaussian distribution is contributing to the probability distribution, and I'll take the weighted sum as my final probability for xn. So let us also further introduce a k-dimensional binary random variable z, which is actually what I have already spoke about earlier in the earlier slides. So this random variable z, it will have a 1 out of k representation. So this means that each one of these z over here is actually a vector of z1 all the way to zk. And here we are going to have every one of these z, each one of the element in the vector z, to take 0 or 1, and which we denote as this notation over here. Zk means the kth element has to be either 0 or 1. And similarly to the assignment variable r that we have looked at in the k-mean assignment, the sum of all the z's must be equals to 1. This means that when zk is equals to 1, we are assigning that particular random variable of x to take the kth class. So this means that we are assigning this to take the kth class. And here we are only allowing it to take 1 out of k classes. This means that all the rest of it needs to be 0, where j is not equals to k. Hence, the sum of all the k needs to be equals to 1. So there are k possible states for the vector c according to the which element is non-zero. This means that it's also otherwise known as a one-hot vector, where it can look something like this. Z is going to be 0, 1, 0, 0, for example, and then you can also have 1, 0, 0, 0, and so on and so forth, where altogether in this example we have 4 different combinations where 1 can be found in any of these entries out of the 4 different positions here. And different from what we have seen in the k-mean example, where r is also a 1 out of k coding, where r is a deterministic value or a deterministic parameter or variable, where there's no uncertainty added to it. So in this case here, since we are talking about probabilistic modeling, we will assign a certain probabilistic distribution to z, and we can see that since z is a 1 out of k coding, so this is 1 of k coding. So what this means is that z, the marginal distribution of z, p of z, is equivalent to a categorical distribution with mixing coefficients k. So this means that if I were to look at z over here, the probability of z, if taking each one of these classes, there's going to be a certain value. So this is, for example, k equals to 1, 2, 3, and 4. It's going to have a certain value where all these parameters or all these probabilities is going to sum out to 1. So I'm going to use a categorical distribution to model this marginal distribution of z, which is given by the product of pi k to the power of zk equals to, which can also be shorthand into this way as we have seen in lecture 1. So in this case here, if I were to say that zk equals to 2 equals to 1, that means that zk is assigning the assignment is going to be assigning it to the random variable of x to the second class, and it will have a certain probability value that corresponds to pi k equals to 2. So this is where the probabilistic value of this assignment going to be happening, where pi here is what we call the mixing coefficient, and as I mentioned, since it follows the categorical distribution, or this parameter is the underlying distribution of the categorical distribution, it must be between 0 and 1, and it must also sum out to be equals to 1. And the next thing that we are going to define for the Gaussian mixture distribution would be a conditional distribution of x given a particular value of z is a Gaussian, since this is a Gaussian mixture model. So suppose that zk equals to 1. This means that I'm assigning x here to the kth class, and we'll assign this as we'll define this conditional probability distribution to be a Gaussian distribution over here. And since we are setting zk equals to 1, this means that this normal distribution that we are defining here would be the kth Gaussian distribution in our mixture model, or it belongs to the it is actually describing the kth cluster in our data distribution, which can also be rewritten into this form here, where we simply ignore without the assignment of zk to be taking any certain class. In general, we will write the conditional probability distribution as the probability of x conditioned upon z, conditioned upon all the classes, and this would be given also to be something similar like a categorical distribution, but now the probability distribution of each category is given by my normal distribution that corresponds to that particular category. So here it will be a product of all the components of my Gaussian distribution raised to the power of zk, where we can see that if zk here in the kth class is equals to 1 and all the rest should be equals to 0, I'm actually taking the probability from the normal distribution of the kth class here. Now, the joint probability distribution, having defined the marginal probability of z, the assignment random variable, as well as the conditional probability of x conditioned upon z, we can look at the joint probability distribution of x and z is given by the following directed graphical model here, where we can see that this is x over here. So in our case, where we observe all the x, so this is actually an observed random variable, and it's conditioned upon z, where z is the latent random variable that defines the assignment to the clusters. We can see that this directed graphical model here, it makes sense because what it means is that we're drawing samples from the clusters, the underlying distributions of the clusters, and each one of these samples that we observe are directly a result of all the respective clusters that we saw, that we know in the probability distribution, and hence the joint probability distribution is given by this the conditional probability of x on z, as well as the prior distribution of z. And since we have defined these two terms here in the earlier slides, we can plug them in and define and solve for the probability distribution of the likelihood. So the likelihood here would refer to the probability of x, since we observe x, and this would be the likelihood distribution. So to be more specific, this should be x conditioned upon theta, where theta here is simply our unknown parameters of pi, sigma, and mu, which is the mixing coefficient, as well as the mu and sigma of our Gaussian or mixture Gaussian probability distribution. And here, since we are after the likelihood, this means that we have to marginalize away the latent random variable, or the nuisance variable of z. Hence, it will be a marginalization over the factorized form of the joint probability distribution of p of x and z here in this case here. Then by plugging in all the definitions of pz as well as the conditional probability of x and z, we get these particular expressions over here, which can then be further simplified into this form. So now here, since we are marginalizing away over z over all the states of z on this term here, on this product term over here, so we can see that the first case here would be to marginalize over zk equals to 1 is 1, and then all the way until marginalizing over zk equals to the kth class equals to 1. And we can see that in this case, since zk here is going to take, it's going to be in this product term over here, we'll see that it's a product over all the kth classes in our distribution, or in our mixture Gaussian probability distribution. And since we are after in this element over here, in this term over here, we're after the case where k equals to 1 equals to 1. That means that it's taking a class of the first in the clusters, and what it means here is that in this product term, only one of this term is going to survive over here. So since this is raised to the power of zk, so when it's 1, this means that I have this term over here, and all the rest where it's 0 in this product term, it will become 1, and hence as a result, when zk equals to 1 equals to 1, I will get this particular term over here, and all the way until zk equals to kth class equals to 1, I'll get this particular term over here. So we can see that as a result of this expansion of the expression over here, we'll be able to get a sum over k of this mixture normal distribution of the components of the normal distribution multiplied by the mixing coefficient. And this as a result would be our likelihood px to our Gaussian mixture model. So this is our Gaussian mixture model over here. Now, another quality of the Gaussian mixture model that we have to define now, we will see that it plays an important role when we solve for the that particular joint probability distribution of x, z conditional upon theta using the EM algorithm, is what we call the responsibility function, where we define it to be gamma zk, and this is simply the conditional probability of zk equals to 1. This means that I'm assigning x to the kth class over here, and condition upon that we have observed this guy. This is our observed random variable, and applying Bayes' theorem to this conditional probability, this is the result that we will get. So this is our posterior distribution over the latent random variable, and we can see that we can flip this term around to get the likelihood here, where it becomes the observed term x condition upon z equals to k equals to 1 multiplied by the prior probability. And then of course we have to have a normalizer over here. We have to normalize it over all the sum of all the k classes here. And now in this case here, we can see that the first prior term here, since we have zk equals to 1, this if we refer back to our prior probability of z, is actually equals to this k multiplied by k to the power of zk. So this is our categorical distribution. It's our categorical distribution on zk here. And since we are talking about zk equals to 1, this means that we are taking the kth class, and all the rest of the term becomes 1, except for the kth class. It has a pi k, so we have this mixing coefficient here, as well as x condition upon zk equals to 1. So if we recall that this guy over here, x condition upon z, is actually equals to our it's the same form of product over k, and the normal distribution of x condition upon mu k sigma k raised to the power of zk. So in this case, since we are looking at zk equals to 1, all the terms will be 1, except for the kth class, where zk equals to 1. What will remain here would be this term over here. And similarly for the normalizer, it's we'll simply take the numerator, and marginalize it over all the k classes over here. Now we'll see that in order to learn the unknown parameters, to infer the unknown parameters in the log likelihood, we can actually take the maximal log likelihood, which is given by this term over here. But here, what happens here is that we will see that since we have the latent random variable of z, which is our unknown or our latent assignment random variable, we will also face with the chicken and egg problem that we have seen in the previous k-mean example here. But in this case, if we were to take the maximal log likelihood directly on this the joint distribution here, we'll see that this ends up to be a case where we would have a incomplete data which involves a marginalization over Zn. So now let's more formally look at the math behind this. Suppose that we have a data set of n identically distributed and independent observations, x1 to xn over here, where each one of the x is in the d dimension. And here we further assume that each one of these observation is drawn from an unknown cluster distribution or unknown mixture model distribution, where we want to first solve for the unknown parameter theta that models the underlying distribution of these observations, as well as we also want to know each one of these random variable, how is it assigned or how is it associated to the respective distribution that we are interested in or the respective underlying distribution. And we can first solve for the unknown parameters by taking the maximal log likelihood as this guy over here. So we can do argmax over theta here as what we have learned in lecture 6. So this would be all our observation x1 to xn conditioned upon the unknown parameter of the underlying distribution theta. But in this case here, we can see that since the overall distribution is actually given by pxz conditioned upon theta, where there is an additional set of latent random variable in comparison to what we have learned in lecture 6, where all these random variables here are observed, and the only unknown would be the unknown parameters here that we need to learn. And in those cases, we can see that it's easy to do the learning, but in this case here, we have the latent random parameters which evaluates this argmax term or this log likelihood term to this term over here. So we have to first marginalize away all the Nielsen random variable or the latent random variable. So the marginalization of this guy over here would be equivalent to the probability of xn conditioned upon theta, since we are marginalizing over all the unknown or the latent random variable, and this would become our log likelihood here. But since we have incomplete data, this means that we are not observing, we do not know, this is unknown. This is our latent random variable. It's a latent random variable that we do not know, and hence we have to tackle this particular summation over here, which we can further evaluate into this particular term over here. This is simply what we have seen earlier, the categorical distribution as well as the mixture model distribution, and finally we'll end up with the Gaussian mixture model here. So in this case here, we have to take the log likelihood over the Gaussian mixture model, where the unknown parameter would be given by theta, and it consists of the set of mixing coefficient. So this is our mixing coefficients, as well as all the mu's and sigmas of our normal distributions. Now we can also see that the joint distribution of pxz conditioned upon theta, where z is the latent random variable and theta is our unknown parameters, can be represented by this Bayesian network over here, where we can see that z directly gives rise to xn over here, and there's a plated notation because we have NIID observations of x over here, where each one of these x is following a normal distribution denoted by mu and sigma, as well as each one of these z over here, it follows a categorical distribution, which is parameterized by the pi over here, which is the mixing coefficient, treated as the mixing coefficient here. So we'll learn how to find or compute the unknown assignment latent random variable, as well as the unknown parameter that characterizes this distribution over here. And we can here we can see that the one intuitive way or one direct way would be simply to take the argmax over theta of the log likelihood, where we'll end up with this complicated distribution, or we'll end up with a complicated expression over here, which involves a log of over a sum of the mixture or the Gaussian mixture model here. And we can see that what happens here is that the sum, the summation, is inside the log term, which we cannot push in the summation, or we cannot push in the logarithm into the summation term, as what we have done previously, where if in this case here, this guy here would be pi, would be a product over n, and the log over n can be pushed into pi, or pushed into the product to become summation n and log. But in this case here, we can't do this. We can't push the log term into the summation term. And what this means is that since we cannot further push the log term into the summation term, the argmax over all these parameters means that all the parameters will be coupled together. After we take the argmax by doing a partial differentiation with respect to pi, with respect to mu, and as well as with respect to sigma, all this differentiation here, we will see that all the parameters here, due to this log term outside the summation term, they will all be coupled together. And what this means is that we will no longer be able to obtain a closed form solution, as what we have seen in the previous lecture, where we are simply after argmax of theta over p of x and this guy over here, where we can see that all the parameters here, the respective parameter that we are interested in, because the summation term, because this guy here is going to be, we are going to take the log likelihood over here, and we can simply push in the log terms into here, and this, we can see that these terms actually decouples all the random parameters or the unknown parameters, such that it's enough to look at the sufficient statistics to solve this problem. But here we can see that in this case here, since the log is outside the summation term, every one of these terms is going to be coupled together, and it becomes tedious to solve. So, but we'll still attempt to directly differentiate this, and we'll see what's the outcome here. So the intuitive way would be to first differentiate this guy here, the log likelihood, with respect to mu. We have three parameters: mu, sigma, as well as pi, which is our mixing coefficient. So we'll look at it, and each one of these mu is actually a set of k parameters, because we have k number of mixing or mixture model. So it's mu1 all the way to mu k here, for example. And now we are going to differentiate this with respect to one of the mu, or one of the mu k's, which we have denoted here, of the Gaussian components, and we'll set it to 0. And this is what we'll get. This is the end result that we'll get. And interestingly, we see that the responsibility term that we have defined here in the earlier part of the lecture, it appears in this derivative after we have set it to 0. So let's collectively call this term over here as the responsibility, or simply denoted by gamma znk here. So we'll shift this, we'll make mu k the subject, and we'll see that this is the final result that we'll get, where it's simply the sum of the responsibility multiplied by all the observation divided by nk, which we have defined to be the sum of all the responsibility terms. And what's interesting here is that although we get the final solution of mu k here, we can see that this mu k, it's also a function of itself, as well as all the other parameters in the expression here. And this means that this is not a closed form solution, since the responsibility is a function of all the other parameters and itself. And similarly, if we were to set the derivative of the log likelihood with respect to sigma k to 0, this is what we will get here. And we will also see that in this term here, we will get a term which is dependent on the responsibility, as well as this term here, which is the sum over all the responsibilities. It is also a function of all the other parameters, including itself, and hence it's not a closed form solution. We can finally also maximize the log likelihood with respect to the mixing coefficient pi k subjected to this constraint here, where all the probability should sum up to 1 by maximizing the following auxiliary function, and where this guy here is the Lagrange multiplier that we have seen in the previous lecture, and differentiating this with respect to pi and with respect to lambda here, and equating everything to 0 and solving for the equation, we will get this expression over here. We'll get this expression where we solve for, so this is solving for the log probability, the log likelihood with respect to pi k, and this guy over here is solving for the log probability, or this Lagrange, let's collectively call this L. So the del of L divided by del of lambda, and equating it to 0, this is what we will get. So we can solve for lambda and then substitute this back into this equation here. And we can see that the final solution that we get for the mixing coefficient is nk divided by n, where again this is a function of the responsibility, which is also a function of all the parameters including itself. Hence, it's not a closed form solution. And but what's interesting here is that the mixing coefficient is equivalent to the average responsibility that each one of the kth component takes for explaining the data point. Now, the maximum likelihood estimates the unknown parameters, and it do not constitute a closed form solution because of the responsibility. This is a function of all the parameters that we have seen in our mixture model. However, what's interesting here is that these results do suggest a simple iterative scheme for finding a solution to the maximal likelihood problem. So here, the simple solution here, or a very straightforward solution here, would be that we do an iterative iteration over the solution to get the solution. And here, the first step here would be to initialize all the unknown parameters, mu k, sigma k, as well as pi k, to a certain value. And then in the next step, or we call the expectation step, we'll evaluate the responsibility term, which is defined by this expression over here, where we'll simply use mu k, we'll simply take mu k, sigma k, and pi k to be what we have evaluated in the previous step, or in this case here, to be what we have initialized in the first step here. So we'll compute this responsibility function, and this, note that this is actually an n by k table, where each entry is simply this responsibility, where it's nk equals to 1 condition upon xn over here. So this is equivalent to the probability value of nk, which is similar to r that we have seen earlier, but now we are not saying that every one of these value would take 1 or 0. It actually takes a certain probability value. So suppose that I'm looking at the xn, the nth entry here, where this is each one of the column is 1 to k, and what I'm saying here is that each one of these has a certain probability. Suppose that this is the case where I'm looking at p of z n k equals to 1 condition upon xn. This has a certain probability value, as well as the second entry here. It's going to p of z n k equals to 2 equals to 1 condition upon xn. There's also a certain value, and all of these values in each row should sum up to 1, since this follows the categorical distribution. And then finally, in the third step, or otherwise known as the maximization step, since we already have the estimates of the posterior distribution over the latent random variable, that's z condition upon x. So since we already have this and the theta, where this theta it's what we have initialized, we call theta O in the previous step over here, and we evaluate this probability in the expectation step. So this means that we already have the responsibility computed from the expectation step, and the next thing to do would be to simply compute or update all the parameters after the maximization of the log likelihood, as we have derived in the previous slides. So here we'll simply take all these terms here, the responsibility terms here, from the expectation step and keep it fixed, and then we'll update all the unknown parameters, and by doing this iteratively, we will get until it converge, we will get both the assignment probabilities. That means that we will get the latent the probability distribution over Z, as well as we will also get the unknown parameters. And the termination condition to this would be the check for convergence. We will evaluate the log likelihood of this, and we will terminate as long as the log likelihood can no longer be maximized. This means that the log likelihood in the time step t is almost the same as the log likelihood computed in the time step of t plus 1. Or otherwise, we can also check for the parameters, all these parameters, if in the case where, for example, t and pi of t plus 1, if I were to take the difference of this, it's lesser than a certain threshold, then I will say that it has converged. Similarly for all the other parameters, and I will terminate the expectation maximization algorithm. So here's an illustration of the expectation maximization algorithm. We'll initialize mu k and sigma k in this and pi k in the two-dimensional example. This means that I only have mu 1 and mu 2, as well as sigma 1, sigma 2, and pi 1, pi 2. And because I have a mixture of two Gaussian distribution, and here I'll randomly initialize mu k and sigma k to identity, and then I will randomly initialize the mixing coefficient to be 0.5. This means that there's an equal weightage of both the Gaussian distribution. And in the first iteration, I'll compute the responsibility, which is the PZ condition upon X. Of course, here would be theta O. This means that I'm directly evaluating this probability distribution, which can be evaluated using the this particular Bayes rule, where I simply flip this guy here and then sum over everything, the normalizer, where I simply this is the P of Z would be simply my categorical distribution, where since I already have theta O, this means that my pi, my mixing coefficient in this categorical distribution will be known, and I can simply compute this probability as a n by k table, as well as I will be able to compute this guy here, which follows the normal distribution, simply just a normal distribution. And since I have the mu and sigma from the previous iteration, I can easily compute this normal distribution, which would also be a n by k table over here. And once I get the probability distribution of the latent random variable, the posterior distribution of this guy, I'll be able to solve for the maximization step, where I simply take the partial differentiation and equate it to 0, where I'll be able to update mu, nu, sigma, nu, and pi, nu in my maximization step, according to the posterior distribution of the latent random variable that I have evaluated earlier. And we can see that after this computation of the update of these unknown parameters, we'll see that the distribution here of the parameters becomes closer to the true distribution, and we will iterate this until convergence. We can see that finally, after 20 iterations, that the distribution of this Gaussian mixture model, it reveals the two clusters in the data set. Now, one important thing to note for the expectation maximization algorithm for the Gaussian mixture model is that the initialization of all the unknown parameters is extremely important because the algorithm is extremely sensitive to the initialization, much more than the k-mean algorithm. So normally what we'll do is that we'll run the k-mean algorithms to find the suitable initialization for the EM algorithm, and then subsequently refine the optimization using the expectation maximization algorithm. It's also important to note that this is useful because if we randomly initialize the GMM, the unknown parameters for the GMM, the EM algorithm, two things might happen. One is that the EM algorithm might not converge to the correct solution. It will always converge, as we'll see later in the proof, but it might not converge to the correct solution. And another thing is that a substantially wrong solution or a substantially wrong initialization might lead to EM converging very slowly. This means that it will need many more iterations and significantly more computations for it to converge to the correct solution. But naturally, the EM algorithm would be able to produce a better solution compared to the k-mean algorithm because because it's based on the soft assignment. This means that we are not doing a hard assignment, or which means that in any iteration, since it's a soft assignment, it will be able to correct for the wrong assignments. But in the k-mean, it will converge very fast. But what it also means is that since it's a hard assignment here, k-mean is a hard assignment, so this means that the algorithm can get stuck in the wrong assignment, and it will not be able to recover